In this video, we will begin our discussion of L'Hopital's rule by looking at a motivating example. So recall that the example given here, the limit as x approaches 0 of sine x over x. This is something encountered in Calculus 1 when we differentiate the trig functions sine and cosine. Now the difficulty with this example is that when you think about x going to 0, what that tells us is that the denominator x is of course going to 0. Sine is a continuous function, so the limit as x approaches 0 of sine x is sine of 0, which also goes to 0. So we cannot simply plug in 0. Instead, some type of algebraic manipulation must be required. But there is no obvious algebraic manipulation that we see. Now in Calculus 1, we are told that the value of this limit is 1. And a geometric argument may or may not have been used to justify the value of this limit. What we are going to see in this video is a little bit of intuition via L'Hopital's rule as to why we can expect the value of this limit to be 1. So L'Hopital's rule, at least the first version of it, tells us the following. If we are evaluating the limit as x approaches a of a function f and a function g, and they both have a limit of 0. Think, for example, in this limit below, the limit as x approaches 0 of sine x is 0, the limit as x approaches 0 of x is equal to 0. Then as long as the limit as x approaches a of f prime over g prime exists, we can use that to replace the limit as x approaches a of f over g. So let's just see in this motivating example how we can put this to work for us. We have the limit that we've indicated on the previous slide. As x goes to 0, sine x goes to 0, and x goes to 0. So we're exactly in the situation that we would like to be in. And what we are going to do here is apply L'Hopital's rule. Whenever we apply L'Hopital's rule, we will indicate we are doing so by simply writing an LH over the equal sign. This becomes the limit as x approaches 0, and what L'Hopital's rule tells us is we can simply differentiate the function in the top and differentiate the function in the bottom, and then that resulting limit will have the same value. So derivative of sine is cosine, derivative of x is 1. Now that we have applied L'Hopital's rule, we can simply plug in 0. Because cosine is continuous. So cosine 0 over 1, and the value of the limit, as it should be, is 1. Let's look at a few more examples. Let's evaluate the limit as x approaches 0 of tangent of 2x over natural log of 1 plus x. And I'm going to note immediately this is not a limit that we previously could have handled. We first want to think about individually in the top and the bottom, what is happening as x approaches 0? Well, both of those are continuous functions, so the top would go to tangent of 0, which is 0, and the bottom is going to go to natural log of 1, which is 0. So we have this, what we might think of as an indeterminate form of type 0 over 0, so we can apply L'Hopital's rule. So L'Hopital's rule tells us that this will be equivalent to the limit as x approaches 0, where we take the derivative in the top, divide it by the derivative of the bottom. So in the top, the derivative by the chain rule is 2 secant squared of 2x. And in the bottom, 1 over 1 plus x. And at this point, if we think about plugging in x equals 0, we're going to get back something non-zero in the bottom, which tells us that we can go ahead and use our limit laws. That is to say, we can take the limit as x approaches 0 in the top and divide by the limit as x approaches 0 in the bottom. In the top, when we plug in x equals 0, secant of 0 is 1, so we're left with a 2, and in the bottom, a 1. So the value of this limit using L'Hopital's rule is the number 2. So one more example looking at this kind of base case of L'Hopital's rule. So individually thinking about the top and the bottom. As x goes to 0, the top goes to tangent of 0 minus 0, which is 0, and the bottom goes to 0 cubed, which is 0. So the intuition to get started is to just individually think, what is the limit of the function in the top? What is the limit of the function in the bottom? If both of those limits are 0, then we can try L'Hopital's rule. So L'Hopital's rule tells us that this will be the limit as x approaches 0. We take the derivative in the top, so that would be secant squared x minus 1, divided by the derivative in the bottom. At this point, we think of being kind of back at step 1. We have a limit we would like to evaluate. So we think, what's happening as we plug in x equals 0? Well, secant of 0 is 1, so the top is going to 0, 1 minus 1. The bottom is also going to 0. Well, if we have something of this form, where the top is going to 0, the bottom going to 0, the ideal thing to do is to apply L'Hopital's rule. And note, each time we do so, which we can certainly do more than once, we indicate that we have applied L'Hopital's rule by putting an LH above the equal sign. So this will become the limit as x approaches 0, and we take the derivative in the top over the derivative in the bottom. So the derivative of the bottom is the easy one here, 6x. In the top, to differentiate secant squared, we need to use the chain rule. And I'm going to go ahead and just write down that derivative below. So the derivative of secant squared by the chain rule, the 2 comes down front, the new power of secant is 1, and then we multiply by the derivative of secant tangent. And if we combine terms just a bit here, the derivative of secant squared is 2 secant squared tangent. So in the top, we have 2 secant squared tangent and minus the derivative of 1, which would be subtracting away a 0. So hopefully now we're good to go. So individually, once again, think what happens to the top and the bottom. As x approaches 0, that tangent in the top makes the top go to 0, and the 6x in the bottom, well, that's also going to go to 0. So it's worked well twice, why not try it again? So applying L'Hopital's rule a third time, this becomes the limit as x approaches 0, and we once again need to differentiate the top and then divide by the derivative of the bottom. So in the bottom, the derivative of 6. X is 6. And that's looking awfully nice if we consider that as x goes to 0, 6 does not go to 0. So this will hopefully be our last application of L'Hopital's rule. So to differentiate in the top, we have a product. 2 secant squared times tangent. So we'll use the product rule. So we take the derivative of 2 secant squared. If we look below, that will be 4 secant squared times tangent. But we're also multiplying that by the tangent, which is already there. So tangent squared plus 2 secant squared times the derivative of tangent, which is another secant squared. Now when we think about plugging in x equals 0, we're going to have 6 in the bottom. And when we plug x equals 0 into the top, because of this tangent of x, that first part is going to go to 0. And then remember, secant of x actually goes to 1. So this second piece goes to 2 times 1 times 1, or 2, and 2 6 is 1/3. And this example illustrates a very important point. It is possible for us to use L'Hopital's rule more than once. And how many times do we use it? As many as we need to get it down to the point where we have limits that we can evaluate.